Here. Welcome everyone to another OCP tap call. This is call number 134. Before we start with the presentation, we have an announcement about a new work stream, and I will hand it to Ankur to introduce his new work stream. Ankur?
Thank you, Ahmad. Hi, everyone. I'm Ankur Sharma from Equinix. And before I introduce the work stream, I want to take a moment to thank a few people who made this possible. Uh, a, a big thank you to Ahmad, of course, for his encouragement and support in launching this initiative, and to the OCP TAP admin team for quickly setting up all the tools from the Zoom to the wiki, calendar, email, shared drive access. Their help behind the scenes made this launch actually seamless. So now I'm excited to introduce a new workstream tab under the tab called Unified Intelligent Infrastructure, or UII in short. So this workstream, let me move to the next slide. Yeah, so this workstream was created from the growing realization that, artificial intelligence, clouds, data centers, and emerging technologies like quantum computing are no longer isolated domains. They are converging not just at the application layer, but in how we architect, synchronize, and scale the systems globally. So at the same time, new challenges are emerging around timing, observability, intelligent workload placement, and system interoperability, especially as we operate across hybrid multi-cloud environments and prepare for distributed, time-sensitive, and quantum-aware compute platforms. So UII is a collaborative space to explore all of this. And we will be diving into questions like, how can we place AI workloads intelligently across edge, cloud, and core? What does observability first infrastructure looks like in real-time multi-cloud environments? How do awareness and network architecture shape performance and reliability? And how do we prepare for emerging paradigms like quantum and neuromorphic computing while building practical systems today? So this isn't just a discussion group. We are building a platform for open collaboration across infrastructure architects, AI engineers, cloud providers, and academic researchers. We'll publish reference patterns, run community sessions, and share practical insights from across the stack. Just to announce also, our first session for this work stream is going to happen on June 11th, which will feature Brad Gregory, who will speak about architecting AI at the edge and why network placement actually matters. This is a perfect example of the kind of cross-domain thinking we want to highlight. So if you're working on AI infrastructure observability, timing, quantum, or you're just curious about what's next, I invite you to join us. And please check out the links here for the wiki and join the mailing list. And let's build this together. Thank you.
Wonderful. Thank you very much, Ankur. So now we'll go for our main presentation. So, Mark, if you can share the slides. So, starting with the intro, it's my pleasure to introduce Dr. Mark Weiss, a leading expert in time and frequency systems. Dr. Weiss spent 35 years at the National Institute of Standard and Technology, known as NIST, where he specialized in time transfer, clock statistics, synchronization, and GPS-based timing. He led NIST support for the GPS program office from 1980 to 2014 and pioneered numerous advancements in the field, including smart clock algorithm. Dr. Weiss has received multiple honors, including the NBS Applied Research Award and NIST William P. Slitcher Award for fostering industry partnership, and the Marcel Akabert Lifetime Achievement Award for his foundational contribution to precision time and synchronization. In 1992, Mark founded the workshop on synchronization and time systems, known as WSTS, and continued to lead it until today. And since he retired from NIST, he has been consulting with a focus on alternative PNT systems. Please join me in welcoming Dr. Weiss.
Thank you, Ahmad, and welcome everyone. I'm gonna talk about an issue that has a lot of implications: time transfer and ensembles across moving platforms. And I'm going to start this out at a pretty simple level, talking about what is this time standard that we work with? Where does it come from? How does it work? And why is it important? what is it, how do we transfer time? What does this even mean to transfer time? And what are the problems associated with transferring time? And why is it an issue that if you have moving systems and you're trying to synchronize clocks, say between a satellite and the Earth, or between two automobiles on the road, why is that an issue? Why does that even matter? And what is an ensemble? And why do we care about that? Oh, a bunch of stuff. I want to give special thanks to Charles Barry of Luminous Cyber Corporation for his collaboration with me, and the PNTP standard that I'm going to be talking about, and also to Dr. Stephen Wilkinson of Raytheon Technologies, with whom I have collaborated with on a lot of the topics that we're going to be talking about today. So that's the opening slide. Let me get my system working. There we go. Here's an outline of what I'm going to do. So I'll talk, as I said, I'm going to talk about precision. What is time and frequency? Who needs it? What does it mean that GNSS are vulnerable? A lot of people know this, and how can time synchronization reduce overdependence on global navigation satellite systems? What is time transfer? How does it work? One way versus two way? Different effects, relativistic effects. And what is this PNTP? That's something that you may not have heard of. And I'm going to introduce that. And then timescale ensembles. What is an ensemble? What is it? Why do we care about these things? What's important about them? And finally, I'm going to end up with a whole lot of research questions, because it turns out there's a whole lot of things that we don't know how to do optimally, and that will make a big difference for the future of our technology. Okay, so moving on here. Where does time and frequency come from? Is that what it is? No, that's the next slide. Okay. Okay, the first thing I will say is that a clock produces a frequency. The fundamental thing a clock does is not produce time. At least the kinds of clocks that we're dealing with in engineering and in precision timing systems, fundamentally, a clock is a system that realizes a principle of physics that says that this system, realizing that principle of physics, has states that repeat themselves at a constant rate. And that's how a clock works, that there's for example, the sun rises, the sun rises, the sun rises. That's a clock. That's probably the first clock humans ever understood or noticed, was that the sun rises every day, and it's kind of about the same time every day. And the principle of physics behind that is that a body in motion tends to stay in that uniform motion unless acted upon by outside forces. That's a Newtonian principle of physics. And the Earth rotating is largely, for the most part, a constant rate. Though when we got more precision, we realized that no, it's not that constant. And so we went to the time it takes for the Earth to rotate around the sun, which is the same kind of principle, but it has less interfering effects. So that became the time standard, and eventually we moved to the atom. And through all of this, we have this thing we call time, and time is just produced from frequency by counting the number of cycles. It's like the calendar, how many times has the sun risen, and that's how many days it's been. And one of the issues around this is because frequency is fundamental, all clocks will walk off from each other without bound. Even the best clocks in the world, the best you can do is slow the rate at which they walk off from each other. And then there's this thing called UTC, which is the international standard. And I didn't mean to move ahead quite yet. And local time can be steered to UTC, but there's a whole bunch of sort of contradictory things about UTC that I'll mention. Wrong way. Okay, so again, the time, when I talk about time in this whole talk, it's not the same thing as what we directly experience as human beings. It's a time standard that we create as engineers and scientists, and we completely make up this time. There's nothing absolute about the fact that on my clock it's about 12 minutes after 11. There's no that's a total artifact that humans have created, and in a timing signal, suppose the timing signal is a pulse of an electronic signal that is 1 pulse per second. We put a label on that pulse and say that pulse is second number 33 of this minute hour and blah blah blah, and we count cycles of frequency in clocks. So the purpose, of course, is we have these laws of physics, but that T for time in the laws of physics, that's an idealized time that is perfectly noise-free and perfectly sequential. And in engineering, in reality, that doesn't exist. So since a clock is a frequency device, there's different kinds of noise. And the kind of noise that interferes the least is white noise. And so if it's a frequency device, the best you can do is have white noise on frequency. But white noise on frequency, because we're counting up phases to get time, you're counting up, it's the integral of white noise, which is a random walk. So every time standard at the best all clocks, the best you can do is have a random walk in time as the noise on the time, and the best clocks will walk off from each other without bound. And then, since time standard is artificial, you can't just generate time in any natural way the way you can do frequency. If you have a perfect cesium clock, it produces a perfect frequency no matter where you are. But time, you can't do that artificially. You can't just have a device that produces time. You've got to get it from a source, and it must be transferred from whatever source is the standard that is relevant to what you're doing. There's two things you need to do to transfer time. You need a signal that is not data, a signal that provides a pulse or something that says, this is the time now. And then the question is, what time was it at that now? And that's given by data. So there are two parts to transferring time. A physical signal, which is not data. Data is a very different animal from a signal. And then there's data. Now, UTC is used a lot, but in most cases, you don't need UTC. You need synchronization between different systems. It often, for example, in the telecom industry, you want synchronization between organizations, different companies that are operating the telecom system, and they don't synchronize their clocks across different companies. So everybody synchronizes to UTC as a common source of time without having to link up different companies. Okay, so as I said, a time signal plus data, they're two different things. And this cartoon sort of illustrates that. So the top arrow shows here's the source on the left. This is where you're getting time. The right is the receiving node. This is a very general principle. The source transmits a signal that's received, and at that point, you just know that that is the on time marker that at this instant was on time, but then you need data to give you the name of that. You know, what is the number of nanoseconds since the last one. Okay, so how do you transfer time? Time accuracy. In order to get accurate time from the sender to the receiver, the big issue is how long did it take to get from, if you're sending me a signal, how long does it take to get to me from you? That's time transfer accuracy. And just to give to really emphasize this problem, suppose I tried to send you a letter and tell you it's now 2 p.m., set your watch. Now, I wonder how many people remember what a letter is? You know, this is not an email, this is a physical letter. And maybe some of us are old enough that we remember that. And what you do with a letter is you write it on a piece of paper, you put it in an envelope, you seal it, you drop it in a mailbox, and eventually some guy comes along, picks it up from the mailbox, it's delivered, it's processed, it's eventually delivered to you. How useful is that? How useful is that? Well, you need to know, if you're going to try to use my letter to set your watch, you need to know how long it took to get to you from me, so you know now it's 2 p.m. my time plus the delay. That's the fundamental principle that we're dealing with, only we're dealing with it not over days or hours or minutes. It's nanoseconds or microseconds or milliseconds. That's precision timing. Okay, suppose when you seal the letter, you time-stamped it, and when the person receiving it time-stamped it, and suppose that they both had accurate clocks. Now you could know how long it took to get to you. But of course, if you have accurate clocks, why do you need the letter? So that's sort of a story that I just made up to. That really is how it works, and it really is why it's a problem to transfer time from anywhere to anywhere else. But I will mention that if you're only wanting frequency from the source, then all you need is to know that the delay is the same, and you don't really need to know the delay. So that's a side comment. So who needs precision time? Well, here's a picture that I got from actually a talk from a guy named Flavio, who gave a talk from Cisco when he worked at Cisco, and gave it at my conference, WSTS. And I have this slide. You know, all these different industries need precision time in order to work well. Everything from, you know, all this stuff we use, telecom, electric power, agriculture, vehicles, and then defense and military systems. And now a big thing is industrial automation and cyber physical systems, this whole new thing that is developing, need precision time. And I'm just going to say more about that here. So why do telecom systems need it? Well, there's multiplexing. You know, how do you get a timing signal from multiple sources and mix it so that they overlay each other? And that means that they're coming in at the same rate, which they never are perfectly, and eventually you have to throw away packets or add an extra packet. That's multiplexing. And that's why telecom systems, one of the reasons they need synchronization. Broadcast services, how do you line up audio and visual, right? You have an image for the TV, and you have sound, and they come through different systems, and you've got to line them up. And that's synchronization. Electric power, the flow of power across countries like the United States. How do you make sure that power from one source can line up with power from another, so they add instead of creating heat and burning up systems? Data centers, financial services, location-based services, that's like GPS. Turns out that things that are a billionth of a second long, a nanosecond, become real life sizes because we're sending signals at the speed of light, and the speed of light means that a nanosecond, a billionth of a second, is a foot. You know, how do you, this very abstract concept of a billionth of a second becomes a well-known size of that you want to deal with. Cyber physical systems. Now here we're mixing computers, cyber systems, with physical systems in a way that now in a cyber system, if it makes a mistake, it could destroy data. But now, if you're actually controlling a physical system, if you get the wrong time, you could make something blow up. It could be very dangerous. So cyber physical systems really need precision time. And how, if you're using software for timing, for example, in trades, stock market trades, and you've got a timestamp, when did that trade happen? That trade happens in the middle of a computer. There is a moment in the computer that determines the trade just happened. How do you timestamp when that happened in a computer? You can't do it accurately because computers don't time their operations. So that's a whole other issue. And analysis, aggregation, many things need precision time. Okay, moving ahead here. So how do you disseminate time? If you've got a source at clock 1 and you're trying to get time clock 2 to lock to clock 1, you've got to send a signal. The signal travels from clock 1, and in the medium, like the letter, it gets delayed. There are perturbations. There's measurement noise. Eventually, it gets to clock 2. And if you're and this is called one-way dissemination, and this is actually used in important systems. You probably have heard of GPS. GPS is a one-way timing system, and all of positioning depends on that one way being calibrated well. And how do you possibly do that? The source is a satellite out in space, 20,000 kilometers away from the Earth, and it sends a signal to the Earth, and you want to know the accuracy of the arrival time to nanoseconds for something that is 20,000 kilometers away. How can that possibly work? It's really a miracle that it does. But the satellite is got a clock on it, and that clock is locked to an atomic clock on the satellite, and that time is referenced to UTC via a prediction that has been uploaded to the satellite on order once a day, and yet it keeps nanoseconds well over the day. And not only that, the position, called the ephemeris, of the satellite also needs to be known. And the satellite sends you this signal. Again, that's the pulse that says, I arrived at time X. And it also tells you where the satellite was when it sent it. And the receiver measures the arrival time on its clock, which could be totally off, but it measures the arrival time on its clock from the signals from 4 or more satellites and solves for the 4 unknowns X, Y, Z, and T, or latitude, longitude, height, and time. And this is called generally a PNT system, position, navigation, and timing system. And it really should be TPN because timing is fundamental. The time is what allows you to get your position and to navigate. So it's very cool. And now in the GPS receiver, you actually have a clock that's locked to the receiving clock. And there is, in addition to the noise and the delay, there's the lock loop systematics and noise that have to be managed. So here's a picture of how a receiver works. GNSS is the General Global Navigation Satellite System. GPS was the first. And, the satellite sends the signal, the receiver receives it, determines the time of arrival of the signal, and receiver itself has an oscillator that's locked to the signal as it's receiving, but that's generally an inexpensive quartz oscillator and is very noisy. So you have a cleanup oscillator, which is often a very good quality quartz oscillator that's locked to that. Or if you want better time, many receivers use a rubidium vapor cell, which in itself is locked to a quartz oscillator and outputs time and frequency. So again, everything involves time. Now, another way time is transferred is called two-way. Clock one, so you're really just trying to synchronize two clocks. You don't think of one as the primary and the other as the secondary, or they used to call it master and slave. We decided not to use that language because it was offensive, but still, it's the same principle. Clock one sends a signal, and now in two-way, clock two sends a signal also, and they both go through the same medium, and this method depends on this medium having the same delay in both directions. That means the path is reciprocal. The delay from 1 to 2 is the same as the delay from 2 to 1. Okay, well, so here's the details of how that works. There's a client here that wants to get the time from the server. The client sends a request to the server saying, send me the time. The client, again, this is sending the letter, right? You timestamp when you send it. The server timestamps when it receives the request. It then processes the request, and a little bit later, the server sends the time back to the client saying, here is the time. And when it sends that, it also says the time I sent this was 9 o'clock and 15 milliseconds from 9 o'clock. The client receives that and now has to do some arithmetic. If the delay is the same in both directions and the client then gets all 4 timestamps, there's enough information to determine, what was the round trip time, divide that by 2, and that's the delay from the server to the receiver. The server sent the time at 15 milliseconds after 9, and if you can't do the arithmetic, you know that the delay was now 7.5 milliseconds, and you add that up and you get 25 milliseconds is the total delay. And so the corrected time is now 225 milliseconds after 9 o'clock. That's how two-way works. Okay, another big issue with timing is security and resilience. And I'm bringing this up because I'm going to talk about the problems with GNSS. So a lot of been work. Everybody's heard of cybersecurity. Everybody's got computers, and we all have these programs that monitor our computers for attack. Everybody's got to pay attention that their computer could be attacked. Well, timing is both a signal and data. So the data can be attacked just like any other data system on a computer, and that's cybersecurity. But timing itself has new timing security issues, and the main issues are, how do you know for sure that the signal came from where it was supposed to come from? It could be spoofed. You could actually not be locked to a GPS satellite. You could be locked to some guy with a simulator that's sending out a GPS signal that has stolen your receiver, so you're now locked to this bad guy. Or how do you know that the signal has not been interfered with in some way? So the general way that you solve this is by having redundant systems, having many timing systems if you really need timing security. And you know, UTC is the most commonly used as a reference. It's the legal standard in many countries, and the way you get it, almost everybody gets it from GNSS, and GNSS are very vulnerable. It's very easy to interfere with GNSS signals because everybody knows the code that is the public code. There are secret codes that militaries use that are harder to interfere with, but we still need backup systems. And so here are the spectra of all the GNSS. The major GNSS are GPS, GLONASS from Russia, Galileo is a European system that has been put up, and Compass, or Beidou now it's called, is from China. And then there are regional systems as well. And what's interesting about all of this is that they all have approximately the primary signal, and they almost all require that you first lock on the primary signal before you lock on any of these other frequencies. So it's very easy to jam all of these. You just jam 1575.42 megahertz, and nobody can lock. Or if you're, have more money or time to screw with the signal, you can jam all of these signals. And so I like to say the best feature of GNSS is its worst problem. GNSS signals are extremely reliable, and consequently, we have all these critical infrastructures, that our lives depend on, that rely on timing from GPS or GNSS, and we don't back them up at all because they never fail. Well, they're starting to fail in all kinds of places, and one of the basic things is jamming. Jamming is illegal, but you can get online and order yourself a jammer. Many people that drive vehicles that don't want their bosses to know where they're actually going with their vehicle will get a cigarette lighter jammer that you can buy online, and suddenly GPS doesn't work on the truck, and they don't know why, and they can drive off somewhere and so forth. Spoofing is another big issue with GNSS. As I said, a spoofer counterfeits the GNSS signal, generates a GNSS signal which has more power than the satellite signal, and your receiver will lock on that, and then they pull you off, and it tells you that you have a different time or a different position than what you think you have. And that has become a big problem. For example, in the Ukraine, commercial airlines can't use GNSS anywhere near the Ukraine now. That's a big issue. So we need alternatives. And generally, everybody's trying to get UTC. If what you want is time from GNSS, it turns out you really don't need UTC for many systems. You simply need to synchronize across clocks. And so time transfer, this is one of the major reasons time transfer is very critical to our lives, is that we need alternate timing systems, which are position and navigation systems as well, that can back up GNSS, can take the target off of GPS and GNSS satellites, so that bad guys aren't putting a lot of energy into jamming. Okay, now I'm going to talk about why it's a problem on dynamic systems. So NIST, where I worked, has an ensemble of clocks, a bunch of hydrogen masers, actually, and they also have a cesium primary frequency standard that they use. And they measure them all against each other in the lab, and the computer combines them all into a timescale algorithm and produces a version of UTC that is a prediction, by the way, of what time it's going to be when we know what time UTC is. By the way, UTC, there is no real-time UTC. Any real-time signal that you get that is UTC is a prediction of what time it's going to be 30 days from now, when the true UTC is published, because it's not a real-time system. It's a computed system based on clocks all over the world. And that's a very good thing, but it also means that the best clocks in the world are off by about 5 nanoseconds or so. So UTC, that's an issue. Can we do UTC also generates timescale ensembles. Can you do that across dynamic networks where things are moving unpredictably? So these are the two questions that I'm going to answer, or at least discuss and talk about what are unsolved problems that need research. Okay, so GPS is the best clock synchronization system ever built. Excuse me, I'm a little proud of the US version of GNSS, but it does seem to be performing very well. So time transfer, really, you just need to synchronize two clocks that are remote. It's a means to maintain time across a network. And how do you do that when GPS is unavailable? And then stationary clock ensembles have been used in national labs to improve reference times and to have more reliability. Can we create clock ensembles for dynamic platforms in a system where GNSS is denied? So these are some of the issues that I think are unsolved problems. So how can you combine clocks? You can have individual clocks. The upper left here, you have a picture of a bunch of clocks, and they're all locked to GPS. This is called plesiochronous. They're all locked to the same source. How close are they to each other? Well, there's always errors. So each GPS transmission will have errors in it. You can all lock to the same ground clock. That's the master-slave thing that I talked about, they now use instead of master slave, it's called primary and secondary clocks. You can also have redundancy where clocks are locked to each other in a circle, and that you need to know the delay again. Or you can have multiple clocks measuring against each other where anyone can be the primary clock. And that's what a timescale algorithm does, is it combines all the clocks and generates one time that is common for all of them. So if you've got a dynamic network, though, the delay, you've got to adjust the delay, and if GPS is denied, you want a common time that is maintained across these. And so, you know, besides accounting for the motion of all of these things, you need their relative distance from each other in space in order to get time. There's also relativity, gravitation, and the speed, the velocity changes the clock rates. So if you're doing precision time, you need the three-dimensional range and the relative velocities between the systems. And so colleague Charles Barry has invented this new standard position, navigation, and time protocol. It uses the NTP format and has added to that position, velocity, and acceleration data that are now transferred and explicitly handles time and position distribution, which allows locking to remote systems that are moving, and that still needs work. It's not a standard right now. There's work in the pipeline trying to standardize that. I'm going to say a little more about that. Here are the 4 timestamps that I talked about for two-way time transfer, and PNTP incorporates them. But now if you've got a moving asset and you're trying to lock to that, you need the differential of all 4 timestamps. So you need the velocity and acceleration. And now if they're both moving, you need both. There are also ways. GPS uses time of arrival of a signal, and now you can also use time difference of arrival. So you can now reference anything that's flying, that's sending any signal at all, if you can identify the time of arrival of an edge that's the same edge on 2 different systems. And difference that you get hyperbolic positioning instead of spherical, and that's another way of doing positioning. And now you can have hierarchical ways of doing that, where you transfer the time from space to lower assets all the way down to the user. And so there are ways of doing alternate PNT. Okay, what is a timescale ensemble? Now, I'm going to introduce this concept. So you measure all the clocks against each other. Well, the best you're going to get, if you've got 0 measurement noise, then all the clocks measured against one clock are the most measurements you get. And so you get if you've got n clocks, the most you get are n-1 independent inputs, but a timescale creates an ensemble time which has n outputs. You want the offset of every clock from ensemble time. So a timescale ensemble can't work because you've got n estimates, n-1 measurements of estimating n things. So it actually has to add in a separate equation. Typically what that is optimizing stability. And the advantages are there is no single point of failure. The output does not depend on any single device. You can then detect an error if any clock has an anomaly. It's easy to detect that very rapidly and solve it. And in principle, the output is better than all the contributors, and yet there are still opportunities for improving this. The general outline of this is you get data from a clock ensemble, you measure them all against each other, then you have ensemble time is computed and comes out as a numeric value on a computer, and then you steer a clock to realize the ensemble time. Now, a dynamic clock ensemble means that you've got the dynamic delays and relativistic effects. Each clock measures and corrects itself. It's similar to UTC, but now in a dynamic environment. And there are many places where this could be used. And one of them is in space. If there's a whole proliferation of satellites being launched, the low Earth orbit satellites are being proliferated. If we could create ensembles out of all of these, it would help know where they all are, and we can also have backups to GPS. So I'm going to move on. The relativistic effects are significant from space to ground, between platforms in a geostationary orbit, which is much farther out than GPS. It's about 77 milliseconds between platforms, and you've got to account for the motion and the relativistic effects. So dynamic ensembles can be developed, but there are unsolved problems. And let's move on. Here are the research questions. So how can you optimally estimate delays among randomly moving networks of clocks? And basically what you need are multiple two-way time transfer measurements. But what's the optimal way of doing that? Can PNTP account for all the delays and minimize the number of measurements that need to be made? That's a research question. Second one is, how do you generate an ensemble time that is more stable than all the clocks, even when the statistics of the clocks are very different? And this is a subtle question that, for example, a quartz oscillator has very good short-term stability, and a GNSS receiver has very good long-term. Typically, you lock the receiver, that you lock the quartz to the long-term or the GNSS, and you get the good short-term and the good long-term. But suppose you have a whole bunch of clocks that are very diverse, including a quartz and a GNSS. Can you get the best out of all of these in one ensemble? That's not solved. And now, what about distributed ensembles? Can we optimize the number of measurements and the filtering of range errors by the ensemble? Now, can you have ensembles of ensembles? Where would this be useful? Suppose you've got a city, and the city is an ensemble of clocks. There's a time standard that the city is generating for itself, and the goal is to control the traffic lights so that each car driving through the city has minimal delays. Every single person driving through traffic gets minimal delays across the whole city. And each car is an ensemble of clocks in itself. So now you've got ensembles of ensembles. How can you best do this? And one of the big problems with ensembles is a clock entering and leaving the ensemble can disturb the ensemble. For example, a high weight clock, if a clock has 80% of the weight and it fails, that can disrupt the ensemble time. So that's a problem. And how do you, if you've got, unstable ensembles where clocks are entering and leaving, how do you then estimate the statistics of the clocks as they come in and as they leave with minimal disruption? So that's all the research questions. That's my whole talk. The whole point is that time transfer across moving platforms is extremely important, requires more research, and optimally doing this requires new research. Minimal time transfer delays are important. Distributed timescale ensembles across moving platforms would be very helpful, and we would like collaborators. And that's the end of my talk. This, by the way, is a real Ripley's Believe It or Not cartoon from, I don't know, 1960 something, when Harold Lyons invented it was an ammonia clock, the first atomic clock. And it was just so amazing that it was even more accurate than the movement of the Earth. Now we just take that for granted, and we got leap seconds as a result. And that's the end of my talk. So I will stop here and see if there's any questions that I can answer.
Thank you, Mark. Thank you very much. All right,
Thank
let's
you.
open the floor for questions. Philip.
I have a okay.
Sorry. Let's Philip go and then you go, Hasham.
Sure, no problem.
Awesome talk. This is exactly the type of thing I was hoping for from this group. For the ensembles of moving satellites in particular, is the location, is like tracking and location data needed a priori? Like, do you need at least some good idea of where the spacecraft is before you can introduce it to the ensemble?
So the question, as I'm hearing it, I think of as tracking from the Earth,
Yes.
that there are ground stations telling the satellites where they are. And that's ideal if you can do it, but it's not necessary. If you have cross-link signals, the satellites are sending each other their time, you can actually, there's enough information just from that to determine, because the satellites are obeying Kepler's laws of motion. So it's harder to do with just the cross ranges, but it can be done independently from the ground. And the ideal thing is to have them both, and then you've got duplicated resilience, a more resilient system.
That's the answer I was hoping for. Thank you.
Great.
Hasham?
Yeah. So Mark, in the last 6 months since you first presented this topic,
Yes.
did you see any progress in research or standards for for all these problems you have been highlighting?
I haven't seen much. What I have seen is some progress in standardizing PNTP, and there is a possibility of getting that into an IEEE process, and I'm very glad about that. But in terms of timescale algorithms, there's been a lot of new publications about timescale algorithms, and they don't exactly solve all the problems, but they are addressing this question of optimally combining very different sorts of clocks.
Mhm.
So that's what I know.
In a nutshell, you're saying BNTP has a potential to move along in the standard, but from research point of view, for time scale algorithms is still slow.
There's work done on the aspects of it, some of the aspects that I challenged, but the combination of doing a distributed timescale ensemble on moving platforms, I haven't seen anybody working. Well, actually, there are I'm aware of at least one government person or related government person who's actually on the call, who's working on considering ensembles across satellites. And so there is progress. I'd like to move on to another question if there are any.
Jay, go ahead.
Yes, thanks, Mark. It was really a really good talk. It's interesting. I never thought of like a GPS discipline oscillator as an ensemble. So that made me think about this in a different way. So, there's both accuracy and then there's noise. And so is the best you can do in an ensemble the lowest noise oscillator? Like, because if you're combining like in a GPS discipline oscillator, that's the best you can do is like the lowest, whatever's lowest noise, and it can maybe be slightly worse. So is that an accurate statement?
I want to break down your question into pieces. So starting with a GPS receiver, right? You've got an oscillator that's kind of a cleanup oscillator, and you're getting the short-term stability of the oscillator and the long-term stability of GPS. But what you really want is accuracy, which is different from stability, and that's harder to do. But still, the accuracy is what is the UTC time at the output of the receiver. And now going from that to an ensemble, if instead of having just two clocks, you get the signal that you're trying to lock to, and then you get multiple oscillators that are measured against that signal, and then you can have alternates to UTC that are coming in that you can also use to ensure that UTC is actually UTC, so you get more security. So yes, all of that can be done, but what's the best you can do? I don't know the answer to that. Is it the stability of the best oscillator? But that's there's two different issues. There's stability and there's accuracy. And accuracy is never as good as stability. So yeah, the stability is going to get you the best accuracy, but you can get delays that are uncalibrated. Even though they're stable delays, you can get other errors in, so you need to have all the delays known. Does that answer your question?
Sort of. Like, so with the GPS, GPS is, like you said, very accurate, but it's noisy. And you can you can kind of depend on where it intersects on ADEV plot, you can get it more accurate, so then more stable. And because of that stability, it's more accurate for a given whatever averaging time that you're getting. So the very best accuracy you can get is, and you're limited to the accuracy from that GPS. So if you have multiple systems, can you get you can't get any more accurate than your most accurate, or maybe I guess you're saying it's more complicated because maybe you can add a bunch of accuracies and stabilities.
Accuracy is not stability. So the Allen deviation ADEV tells you stability. So if you have instability impedes accuracy. So yes, you're not going to get better than the most stable clock in your system, but accuracy requires knowing the delay perfectly, or as perfectly as you can get. And the delay from GPS, there's unknowns in there. How long does it take to get through the receiver? And how well has that been calibrated? So all of that means that GNSS has errors that you can never get rid of but how good can it get? It can get down to nanoseconds. But what if you want picoseconds? And so having multiple redundant systems improves the accuracy because the errors are different. The error sources are very different, and you can have a weighted average based on your knowledge of which ones have the worst uncertainties.
Okay, I think I get that. Yeah, thanks. That makes sense.
Yeah.
Well,
I can stay on if people have more questions. We're past the top of the hour.
Yeah, I just have one last question. It's because you said that you're looking for collaboration for the PNTP.
Yes.
how we can collaborate to this, because I'm really interested to have this as a standard, because we are dealing with exactly the same kind of problematic. We are doing our own standard, so which I don't think it's a good idea.
Okay, who is we?
And
I'm not sure who you work for.
Saffron.
Oh,
Electronic and
Saffron.
Defense.
Yes, of course, I know Saffron. Can you contact me? Send me. I think I probably have your email address because
Probably I
were
sent you, I think, long time ago, I sent you an email, but I can resend it to you.
send
But if
it
you,
to me again. I will link it to Charles Barry, who's doing the lead on all this work.
okay. Okay, and just one, why did you use NTP and not PTP? I mean, PTP has a lot of advantage and extensions and many things. Do you know why, or it's
I think it really is just trying to use a standard format for data. The only reason PTP is more accurate than NTP is because PTP has built in hardware timestamping and devices like boundary clocks and transparent clocks that calibrate the delays through systems. But in principle, NTP is as good. So if we're just defining a system that's going to be in line of sight signals, then it doesn't matter whether we use PTP or NTP. And I don't know why he used NTP format, but really we wanted a standard format, and that's the one he chose.
okay.
Great. Hisham, you have another question?
No, I
Your
don't.
hand,
Oh,
your hand is
oh.
still up,
Yeah,
Hisham.
your hand.
But I see
Ah,
Paul
right.
Laurel is
Lower
raising his
hand. Lower hand. I learned.
Okay. And Benoit, you're done also. Anyone else?
Mark, can
Paul,
you hear me?
go ahead, Paul.
Mark, it's good to see you again.
Yes, hi, Paul.
Thank you for an excellent presentation. It was thoroughly well done. So you've described the physics and the math from a special and general relativity perspective. What are your thoughts on quantum mechanics and indefinite causal order in particular?
Oh, God. We've had this discussion, and I really don't know much about it. Quantum mechanics is famous because nobody understands it. Feynman was one of the leaders in quantum mechanics. He got a Nobel Prize for his work. And he said, if you think you understand quantum mechanics, you don't.
That was earlier in his life. Later in his life, before he died, he actually said he thinks he now understands it. But
I think that the problem is the entangled particles and the way they behave completely violates relativity. And both of these are fundamental laws of physics, and they're both proven beyond a doubt that they're both real and they're both true. And yet you can't resolve those differences without reinventing all of physics. So no, I don't understand it.
Thank you. Okay, fine. We are working on the distributed ensemble problem, and we can share the results after the meeting.
Oh, I'd love to talk to you about that. Thank you. And these problems, I'm happy to collaborate with anybody interested. The more the better, because the problems are very complex.
All right. Any more questions before we adjourn? Great. Hearing none, we'll see everyone in a week. We have another a special event in a week that is Ankur basically invited a speaker, and then of course we have like in 2 weeks a regular another call basically from Seth. And with no further ado, Mark, thank you again for your great presentation, and we'll see everyone in the next call.
And I want to thank Ahmad for putting this whole thing together. It's really an amazing series. And the fact that you're 130 something this
Your
one,
134th call.
that's wonderful. Thank you.
Thank you. All right. Bye, everyone.
Bye-bye.